Electric fields. I will cover the basic concept and the concept of electric field in this video. There are two kinds of charges, namely positive and negative charge. Charges of the same sign repel each other, charges of opposite signs attract each other. So the electron has a negative charge, the proton has a positive charge. E is the fundamental charge or the elementary charge. The charge of an electron is minus E. The charge of a proton is plus E. So there are two things that we need to know about conservation and quantization of charge. Conservation of charge means that charges cannot be created or destroyed. Quantization of charge means that the electric charge always occurs as integral multiples of the elementary charge. So which means that you can have two electrons, there's a charge is -2, but you will not have fractional charge. For example, a charge of half E. So that's the meaning of quantization. Everything is in integral multiple of E. The electric field. An electric field is a region of space where a charge will experience an electric force. Similarly, a gravitational field is a region of space where a mass will experience a gravitational force. So what is an electric field? An electric field is a region of space and it has certain property. So what's the property? The property is that a charge will experience an electric force. So next we come to the electric field strength. Electric field strength at a point is the electric force per unit positive charge acting on a small test charge placed at the point. So E is F divided by Q. So the units is Newton per Coulomb in SI unit. That's why the definition is force per unit positive charge. The analogy with gravitational field strength is G. So G is F over M, is force per unit mass. And we get the equation F equal to mg. So G is the gravitational field strength. Okay, example 1. An isolated electron near the surface of the Earth was found to be accelerating directly away from the surface with an acceleration A. So question, what is the direction of the electric field near the surface of the Earth at the location of the electron? In this example, the force on the electron is upwards, away from the surface of the Earth. Hence, the force on the positive charge would be downwards. The direction of the electric field is defined as the direction of the force acting on a positive charge. Therefore, the direction of the electric field near the surface is downwards towards the Earth. So for part B, calculate the magnitude of the electric field near the surface. So by Newton's second law, the force is QE equal to MA. So you can put MA equal to QE, and the electric field will be 1.5 times 10 to the power of -5 Newton per Coulomb. Electric field lines. So we use field lines to represent an electric field. The electric field line must be able to represent the variations in the magnitude and direction of the electric field in a region of space. The number of field lines per unit area through a surface perpendicular to the line is proportional to the magnitude of the electric field. Hence, where the lines are close together, the electric field is strong, and where the lines are far apart, the electric field is weak. The direction of the electric field is shown in figure 7. So the direction of the electric field strength at a point E in the electric field is tangent to the electric field at that point. So there are certain rules for drawing electric field lines as listed in this table 1, 2, and 3. For exam purposes, questions requiring drawing of field lines will look for the following 3 items. Number 1, you have to show the correct direction of the arrow. That's the direction. The number of lines. If you represent Q with 6 lines, then you will need to represent 2Q with 12 lines. And the lines must not intersect. So these are some examples of electric field lines. So for single charge, it radiates in all directions equally. And if it's a positive charge, the direction of the arrow will be away from the charge. If it's negative charge, the direction of the arrow will be towards the charge. So part C, two positive charges equal in magnitude, and part D, two opposite charge equal in magnitude. Now part E show two opposite charges, the magnitude of one charge being twice the magnitude of the other. And F show a pair of oppositely charged parallel plates. Now for part E, you'll notice that there are 6 lines coming from the negative Q, and there should be 12 lines coming out from 2Q. So that's how we represent magnitude by the number of lines. Okay, force between 2-point charges. This is called Coulombs Law. So Coulombs Law states that the force is equal to 1 over 4 pi epsilon 0 Q1 Q2 divided by R squared. Note that this equation is only valid for the case of 2-point charges. Coulombs law has the same form as a gravitational force between two masses, where F is equal to G m1 m2 over R squared. What happens if there are more than 2 charges? The resultant force in any one of them is equal to the vector sum of the forces exerted by the other charges. So you can find the force between 2 charges using Coulombs law, and then after that, you will just add all the forces vectorially. Okay, example 2, 2 small equal charges, one positively and the other negatively charged, are placed at A and B as shown in figure 10. AB is 6 centimeter. Calculate the force acting on the charge of 1 times 10 to the power minus 8 coulomb placed at P. P is 5 centimeter from both charges. The charge at A repels the charge at P with a force F given by F equal to QQ over 4 pi epsilon 0 R squared. So F will be 7.2 times 10 to the power minus 4 Newton. The direction is along AP. The charge at B attracts the charge at P with a force equal to F in the direction of PB. The vertical components of FAP and FBP cancels, hence the resultant force R is horizontal. So the magnitude is given by the sum of the component, which is 2F cosine theta. So you can find cosine theta given by Bx over Vp. So from there, we can find the resultant force, which is 8.64 times 10 to the power of minus 4 Newton. Electric field around a point charge. So we can find the force is QQ over 4 pi epsilon 0 R squared. Electric field is force per unit charge. So it's F over small q, therefore we have Q over 4 pi epsilon 0 R squared. So this electric field belongs to the charge big Q. Now this equation, E equal to 1 over 4 pi epsilon 0 Q over R squared, is valid for point charge. It's also valid for the field outside a spherical conductor, a charged spherical conductor. So note that E is a vector quantity and its direction at a point is given by the direction of the force experienced by a positive charge if it is placed at that point. What if there are multiple charges? In this case, the E field, resultant E field, is the vector sum of all the contributing E field. Example 3, a charge 1.4 microcoulomb and a charge of 2.6 microcoulomb are separated at 15 centimeters from each other. At what point P other than the point at infinity is the resultant electric field 0? This point is known as the neutral point in the field between the two charges. In order for the net force on a small test charge to be 0, the force exerted on the test charge by Q1 and Q2 should be in opposite directions and equal in magnitude. Hence, the test charge must be located at point X somewhere between Q1 and Q2. So let R be the distance of the test charge Q from Q1. So you can calculate the forces exerted by Q1 on the test charge Q, as well as the force exerted by Q2. So from there, we get R equal to 0.063 meters. Okay, this is the end of section 12.1 and 12.2.